All right, so what needs to be done by the end of the day Friday? Yes, that first Connect, which I had the due date set earlier, but it wasn't showing up on Connect for the first couple of days, and I wasn't aware, so that due date kind of got pushed, into the future a little bit. You'll see, I'm not sure if I set it to release before or after class, but the next Connect assignment, and then I'll be posting the next Excel assignment. So originally, I think the exam was going to be next week. I'm going to push it into the future a little bit. Like I say, push it forward, but some people think bringing it forward means closer. I'm pushing it forward. So it'll be like the following week. So I'll put an announcement up on Canvas, but tentatively planning for Wednesday in class, which I believe that is the 29th or 30th. I can't remember the exact date off the top of my head, but I believe I think it's the 29th. So we got a little bit of time leading into that. In those next couple of weeks, we'll have those two assignments that Connect and Excel. It should kind of be some good preparation. Both of those are going to have questions, even the Excel that has some things similar to what we're going to do on the exam. We'll work through the Excel example today that'll look similar to that second Excel assignment. And I'll kind of point out those types of questions you'll see that would be good preparation for the exam. Also, this week we can get up some practice exams, right? So we're still waiting a couple weeks out, moving that exam date, but at least it gives you some materials to start reviewing once you kind of get these homework assignments out of the way. Okay. And for most of them, especially after today, you should be able to get through the majority, if not all of that Excel assignment. And the Connect, you should be able to make pretty far into it. We'll probably cover the last of the material next Monday and Wednesday. So kind of start on those early, start to answer the questions that we've already covered the last week or so here, last week and this week. But that's kind of where we're currently at. So any questions for me before we jump into material today? And we'll talk more about the exam as we get closer to kind of the format and what it's going to look like. Once I have those practice exams, those will look really similar to it. We left off last class, and I told you I was going to put up one of those pre-class videos up on YouTube. So it was up there. It was kind of me working through an example. And basically, we left off talking about this idea of conditional probabilities, right? So this is the multiplication rule. This is the equation we said would give us that conditional probability. And we talked about why that's the case. When we condition on something, it's almost like we're taking the experimental outcome space from 1 down to whatever the probability is of what we've conditioned on, right? If I know that outcome A has occurred, I know that there's certain outcomes that no longer can be realized, right? I've told you A has occurred, so I'm a smaller set of outcomes, right? So now kind of like that's our base or that's our denominator. So I ended last class with that. Here we kind of have a summary of the rules we talked about, this idea of the complement, the addition rule for finding the union of two events, and then this multiplication rule, which helps us find the intersection of two events, or if we rearrange it, helps us find this conditional probability. So that's where we're at, right? So that pre-class video, right, I'm supposed to watch prior to today's class, right? The example I used was which of the following, right? So was it getting at kind of, I had this contingency table, and I was really showing you how to use it to solve for these conditional probabilities, but what was the example? Was it political party affiliation and opinions on marijuana legalization, COVID vaccination and death from COVID, height and income, or gender, and then exam scores? Okay. So if you got logged on and watched even 30 seconds of that, hopefully this shouldn't be too bad. Okay. Might have even mentioned what the example was last class that I was going to do. Yeah, maybe has a little bit of time to get on there. Counted, I think we're a little bit low today. Does everybody get a chance to get an answer on that one? 26 people? All right, I'm gonna ride with that number for the rest of the class. So close this out. So did anybody watch it and wants to say which of these it was? Yeah, right, so I worked through this example where basically my events, A and B, and their complements were whether or not you were vaccinated or not, and then whether or not you died from COVID or didn't, right? So kind of working through that example, if you didn't watch it, I highly suggest to go back and watch it because that's going to show you how to go through a conditional probability, but not use as many examples because that one's out there. But basically, if I want to find a conditional probability and it's just the intersection of two events divided by what I'm conditioned on, those are values I can get from a contingency table. If my events A and B were vaccinated, and A complement, you weren't. B was, did you die? B complement was, did you not? We could solve for a bunch of different conditional probabilities. Right? So kind of putting some general kind of values to this, right? If I wanted to find a conditional probability, right? So here, R1 given C2. Well, if I know the general equation that's going to work for me is that if I want a conditional probability, that's the same as the intersection of those two events divided by what I'm conditioning on. Then when I want the probability of C1, it was in R2, or C1 given, no, R1 given C2. I'm just going to write this out in the context of my example. So the intersection here would be R1 and C2. What I conditioned on, remember, is what's on the right-hand side of that line. So kind of my new space of experimental outcomes is not 1, but it's whatever the probability that I saw C2 was. Because I'm telling you C2 has occurred. Now that you know that, what's the probability R1 has occurred? Well, it might change, right? If those two variables are related at all, right? C1, or the two events, I should say, R1 and C2 are related at all, knowing that R1 has, or C2 has occurred might change the probability that R1. This is the idea of, what's the probability that if I walk outside the building, I slip and fall? Relatively low. Given that it's freezing rain outside, what's the probability I slip and fall when I walk out of the building? Well, now it's changed quite a bit. Okay. So from here, all I do use a contingency table to do is what's R1 and C2? 0.2, right? That's the intersection of those two events. So if I'm, well, I'll write it up here, but no, I won't. 0.2. What's the probability of just seeing C2? 0.5, right? So 0.2 over 0.5 gives me that conditional probability. Now you'll notice here we had an example where the conditional probability, so this is what I would call the conditional probability of R1, right? Is this guy right here. We're still looking for the probability of R1, it's now a conditional probability because it's conditioned on something else happening. If I, for instance, just wanted the probability of R1, I would say this is the unconditional probability of R1. So you can kind of see the unconditional probability, the probability of just R1 would be what? Go to that contingency table, go over the total. 0.6. Probability that R1 occurs is 0.6. That's very different, well, not very, but it is different from the conditional probability of R1, which we found was 0.4. So having this additional piece of information, right, is going to alter what that conditional probability is. Okay? Except for in certain situations, which we'll talk about in just a second. Any questions over kind of how to, we ended with that multiplication rule last class. That video kind of went through an example, not with just like R1, C1, but some actual names to the events. And again, here's one of how we would solve this. So this should be what, 0.4? I think I have the, there we go. Okay. So I think last class I showed you an example where I drew out the visual as to, if you're limiting it down to just event A, well now not as much of event A is the same proportion of also being in B as if we look at the entire experimental outcome space, and that's why conditional and conditional probabilities aren't the same. But there can be a situation, right? So I think I think the example I used there, I'll just draw it out real quick. I won't explain it too much, just kind of a review. Like, let's say this was my event A, was just half of the entire experimental outcome space. Here was event B. Here was kind of their overlap, very small area. So the probability of B is relatively large. But if you tell me, okay, well, what's the probability that B has occurred, given that I know the outcome, right? I know that the outcome is somewhere in A. Well, now it's almost like all these aren't outcomes I could see. Because if I know that A has occurred, I know that I'm somewhere only in this box. Well, now that I know I have to be somewhere in this box, the probability I see an outcome in B, relatively small. So this is the idea that if I have information about event A occurring, it's going to change the probability that I now see event B, right? As opposed to, just no information at all. So we can think of another scenario where instead of these events depending on each other, we'd say that they're independent. Okay? So the true definition of independence is simply that the conditional probability of an event, so conditional probability of A, is equal to the unconditional probability of A, right? Knowing that B has occurred doesn't change the probability at all. So this might be something like, what's the probability? Oh, I used one earlier today. You could probably argue this isn't the case, but to me, this makes sense. Let's say event A, right, is that you are a registered Republican, right? So roughly, I don't know what the percent is, it probably varies by state, but it's somewhere probably between like 35, 40%. So we'll just say the probability that I choose someone at random, they're a registered Republican, is about 0.4, right? Well, now if I told you, okay, well, given that the person is taller than 5'8", well, now what's the probability they're registered Republican? It doesn't change at all, right? The distribution of height is similar across, Republicans and Democrats, right? It's not related at all to political party affiliation. And so having this additional piece of information about the person's height doesn't tell me anything about the probability that they're going to be a registered Republican, registered Democrat, whatever I'm interested in. So the idea of independence is that we have this additional piece of information, but it's from some event or some variable that is completely unrelated to the one that we're interested in. Okay? The way this looks like visually, I'm going to try to give I think this is a little bit different than we've looked at. So instead of circles here, I'm just going to kind of draw some squares or rectangles. So let's say this represents event A, all the outcomes that are in event A, right? And it exactly splits this rectangle, or I try to get close to a square, but whatever, in half, right? Then I've got event B, which kind of cuts this entire experimental outcome in half, in that experimental outcome space in half, but the other direction, right? So the probability of B here is also 0.5. It's just, right, it includes some outcomes that aren't in A and some that are. Okay? So if we're thinking about the intersection of A and B here, well, that's just going to be where these two rectangles cross each other, right? And if I've drawn this to scale, the intersection of those two things is 0.25 here. Okay? So if I wanted to find the probability of, let's do B given A, that's going to be the intersection of those two things divided by what I've conditioned on, so the probability of A. The intersection of A and B, remember, doesn't matter which order I write it in. A and B is the same as B and A. So this intersection is 0.25. And the probability that A occurs is 0.5. So I actually end up with the conditional probability of B was the same as the unconditional probability of B. That's the definition of independence. I would say that these are independent events. And the reason why that is because if you think about it, if I look at the entire experimental outcome space, B made up of half of that space, right? The proportion of the overall space that was in event B was 1/2 or 0.5. When I then condition on A, of the event that I've conditioned on, right, of the space or the outcomes that are in event A, exactly half of them are also in event B. So the proportion of the remaining space that's made up of event B hasn't changed from when I didn't have any information, right? So that unconditional probability and the conditional probability end up being exactly the same. Right? Excuse me, this would be like the idea of, registered Republican and then kind of over 5'8" or whatever height that I'm choosing. Yeah.
Can you do it the other way around too? Because there's like the probability of A given B. Would it be the same answer?
Yeah, it ends up being the exact same just because I made the halves here nice and easy. It doesn't have to be that it's always 1/2 and 1/2. It could be 0.3 and 0.3, right? But you're right. I can show independence by using this guy right here, which is what I did there, that the conditional probability of B is the same as the unconditional. I could have also checked to see is the conditional probability of A the same as the unconditional, right? So both ways will always show me the same answer. They'll either show me their A is independent from B, the other way that B is independent from A, right? Once they're independent events, they're independent from each other. So it doesn't really matter which way I say, is A independent from B or is B independent from A? They either, yes, they're both independent from each other, or no, they're both dependent on each other. That's a good question. Any other questions on this before we keep moving? I'm not going to wait too much. So we can check this idea of independence using our contingency table. But one of the nice things that comes out of this definition of independence is that if I'm thinking about that multiplication rule, right, instead of, we have kind of two forms, right? I can just rearrange it. Here, if I knew the conditional probability but didn't know the intersection, I could use this. If I knew the intersection of the events but didn't know the conditional probability, I could use one of those forms. Right? So if I use this guy right here, my multiplication rule, but then I remember if they are independent, then the probability of B given A should just be the same as the probability of B. So if I plug the probability of B in there, and when I multiply the probability A times the probability of B, if that's the same as the intersection, that means they have to be independent. Because the only way those two things will be equal is if this conditional probability is exactly the same as the unconditional probability. So it's kind of like another way of checking for independence. We can use this method, kind of like how I plug the values in here, or we know that this has to hold as well. So I'll show you how we do all of these kind of using our contingency table. So if we wanted to use the definition of independence, right, we could check either one of these, or we could check both. So we'll check the first one, right, that the conditional probability of A is the same as the unconditional. So what's the conditional probability? Sorry, not conditional. What's the unconditional probability of A here? We got one. So if I ask you for what the probability of A here is, what's that going to be? Yeah, just go over to the total column. It's going to be 0.6. So this is what I'm trying to check to see if it holds, right? So I can plug in that 0.6 there. For my conditional probability, I know I can rewrite that as the intersection of the two events divided by whatever I'm conditioning on, which is on the right-hand side of that line. So the probability of B. What's the intersection of A and B here? What's that probability? Yeah, those top four left cells represent intersections. Go to the row and column heading of A and B, 0.15. What's the probability of B? Okay, let's go down to the total, 0.25. If these two things are equal, we say they're independent events because that would reflect that the conditional and unconditional probability are the same. If I plug this in my calculator, sure enough, I end up finding that these are independent events. Questions on that?
So if it's A and B, B would be on the bottom, like you would divide by.
We always divide by whatever we're conditioning on, which is what's on the right-hand side of that line. So that's what we just did. We could have also done it the other way, right? So we could have said, is the conditional probability of B equal to the unconditional? There, what's kind of weird is because order doesn't matter, what I'd actually end up with, right, is the probability of B and A, but that's the same thing as I had before. It doesn't matter which order I say it when I'm looking at intersections. But now I'd be this second way, right, the guy on the right, I conditioned on event A, so I'd actually need to be dividing by probability of A, not the probability of B. But once I have it written out, I can just find all those values. I can find both of these values from the table. 0.15 over 0.6 ends up being 0.25, which if I'm looking at the unconditional probability of B, it's also 0.25. So it didn't matter which way I checked it, right? They both showed me they were independent. And if they weren't independent, they would show me they're both not independent. Any questions on that? Okay with that? I'll do a little bit more of this once we hop into Excel here today as well. I could have also checked to see if the intersection of these two events was simply equal to the product of each of those events' probabilities, right? Probability A times probability B. So here, we check that, right? The intersection of A and B is 0.15. Right? If that's the same as the probability of A, 0.6 times the probability of B, 0.25, right? Which sure enough it is, that also shows me they're independent. Right? So we got kind of three ways we really could have used this contingency table to check for independence here. Questions on that? Not all of them are valid, so as long as you use one of them. Yeah.
So if like the unconditional probability is A is equal to the conditional probability A or independent?
Yeah.
All right.
Yep. Right. That's kind of goes back. Well, that's really what we're saying here. Right. Or if the conditional probability of A is the same as the unconditional probability of A, you also know the conditional probability of B will be the same as the unconditional probability of B. And knowing that's true, this equation has to hold, right? If they're not independent, then when you're using the unconditional probability of B, you actually should be using the conditional probability of B in here. This only holds because if they're independent, those two things would be the same value, right? So if you ever use this check and find that they're not equal to each other, well, you know that they're not independent, or they're dependent events. Yeah. Any other questions on up to this point? Yeah.
What happens if it is dependent?
So if these two things aren't equal, and we say they're dependent, that's fine. We're just gonna have a little bit more work to do with things, right? In the sense that, now knowing that B has occurred will change the probability that A has occurred, right? My conditional probabilities won't be the same as my own. This is kind of a definitional thing. It makes our life a little bit easier if they are independent. It's a little bit easier to find this intersection because we don't have to like plug in a conditional probability there. Which once we get to doing things like Bayesian Theorem, which I don't know if we'll do there today, but definitely on Monday, makes it a little bit trickier when we don't have independent events. And most things are going to be somewhat dependent, right? I mean, for them to be the exact same probability, you have to have two things that are completely unrelated. So like in my example of height and political party affiliation, I know that there's some research that shows height's correlated with income, and we know income's correlated with political affiliation. So there's probably even that example, two things that don't seem like they'd be related probably aren't completely independent, right? So it's very unlikely we have these independent events. But if we do, it makes our life a lot easier. Now, I'm not going to dive too much into class. So I don't think I don't want to waste too much time. But one thing that kind of is a byproduct of two events being independent, you can go through using a Venn diagram and kind of prove this to yourself, especially if you use like an example like I did over there with the squares. If you just want to think about A and B complement there, and then try to think about the same idea, can I find that the probability of A complement is the same as the probability of A complement given B complement? Right, so I can prove independence of the complements. What ends up always being true, and Google independence complements mathematical proof. You can walk through line by line of mathematical proof that will show you if two events are independent, their complements actually also end up being independent. So, I mean, I won't exploit that too much. I say too much. I won't exploit that in any of your homework questions or exams. I'm not going to, expect that you know that. But at this point, it's something worth kind of mentioning here. It's a nice byproduct of two events being independent is that their complements end up being independent as well. Right? So we could go ahead and prove that to ourselves here. We can find the intersection of the complements, which is 0.3. We can find the probability of each complement, 0.4 and 0.75. 0.4 times 0.75 ends up being the same thing as the intersection of those complements. So the complements here are independent, right? And it'll always be the case. I think I'll come back to this maybe end class on this a little bit. But I do want to make sure we do some work in Excel before we run out of time here. So, I think I've got a few things in here we'll talk about. But basically, the Excel example we're going to look at has to do with unions and then wage differentials. Okay. So, If you go to Canvas under the in-class data folder, I had this union data. It's got one sheet that's blank and then one sheet that's got kind of hopefully what we'll recreate today. Okay. So we'll start working on this blank file. And I've got a couple different kind of variables here. This is more of a business related example or an economics related example. I've got a bunch of different industries. So like architecture, arts and design, business and finance. I've got what the percent of those industries were belonging to a union in different years, okay? So one thing that we think about is the higher the percent of an industry that's unionized, the more power that union has, right? If every worker is a union worker, well, then the companies, in order to have any laborers, right, have to pay the union wage. If a small percent of the workers are unionized, well, instead of paying a union worker a higher wage, I'll just go and find out a non-unionized worker and pay them a lower wage. Right? So as unions get more power, as they have a higher percent of the total like workers within an industry, they can actually argue or they can kind of barter or bargain for higher and higher wages. So this other variable I have is I took union and non-union weekly earnings and I found the difference between the two. Right. So in 2008, in the accommodation industry, or companies that would meet that classification, the difference in union, non-union weekly earnings was $111. Right. And then we can go through all these different, kinds of industries. So what we might be interested in, if I go over here, is I'm going to find the average kind of union membership. So just use that average to find that mean. Go over to my union membership variable, Control Shift or Command Shift on a Mac, hold those two together and hit the down arrow, selects the entire column of data, hit enter. I got the average union membership is about 10.7%. And then the average wage differential across these industries is about $118. Okay. So with this information, right, and this will be something like I would probably do for you ahead of time on the Excel assignment. But I'm going to kind of use those as a place to start and say, okay, my cutoffs that I'm going to use are 10 and 100, right? Just kind of make them nice, easy numbers to look at. Excuse me. So basically, I'll be interested in, is an industry have 10% or higher union workers in that year? Or did it have below? Right? That's kind of like my A and A complement, okay? Or my B and B complement, however you want to think about this. And then the other kind of event I'm interested in is, do they have a wage differential between union and non-union workers of $100 or more, or the complement of that, which is just less than 100. Right? So I kind of had this table already typed out, so we didn't have to waste time watching me type and probably make a bunch of mistakes here. Right? But I've got my event A and A complement and my event B and B complement here. So I've been giving you contingency tables, but where do these probabilities actually come from? Well, if we had some existing data set with some historical data here, I could say based off of the data I have, I can count the number of industries across this time period that had 10% or higher union membership. So I'll kind of think of these as like highly unionized industries. And they also had wage differentials of $100 or more. Okay. Well, how can I count the number of industries in my data set that meet that criteria? I can actually use that COUNT-IFs formula, which you should have been using for that first Excel assignment. We kind of used it when we did that enrollments data. But the way we're going to use it today is a little bit different than when we were doing frequency distributions. So it still needs the same things. You have to tell it which variable to look at and then which criteria you want to be met in order to count that observation. So the very first thing we're going to do is, okay, I want you to go through this union membership variable. So I'm going to Control Shift, hit the down arrow, Command Shift on a Mac, scroll back up so I can show this to you so it's not small like it is up here in the formula bar. All right, so now you can see this. So it says, look through that variable that's in column C, which is that union membership, and count the observation only if it's greater than or equal to, and here it's kind of blocking out what my labels were here, but you can kind of remember it was 10% or higher union membership. So I'm going to use an and sign here. And instead of putting in the number 10, I'm going to select on that cell that I had the cutoff in. And I'll show you how, if you set it up this way, you could actually reproduce this table for any different cutoff that you were interested in. Okay. So go through the data, only count the observation if that industry was 10% or higher unionized. If you want to think about it that way. Almost sounds like euthanized, which is not good. So we've got this criteria has to be met in order for that observation to be counted. But then comma, we also only want to count it if that wage differential variable is greater than $100 or is $100 or more, right? This difference in earnings variable is 100 or more. So I could select this, click the first one, Command Shift or Control Shift, hit the down arrow. But since I can already see that it starts and stops, right, in 2 to 736, and I know that the variable I want is in this column H, so I'm not jumping all around and the screen's moving for you guys. I'm actually just going to type this in, right? H2 and then colon, which means go through H2 all the way up to H736. Right? I could have got that same cell reference in there if I, highlighted this entire variable, but I just typed it in. Okay. And then we only want to count the observation if it had 10% or higher, but also if this difference variable is greater than or equal to, and we had our cutoff for that up here set as 100. Okay. So go through this first variable, which is the union membership, count it if it's greater than or equal to 10, and then go through that wage differential variable and then only count it if that is also greater than or equal to 100. So this should give me the number of industries in my data set that had 10% or higher union membership, and the wage differential was over $100 or more. Okay. Any questions on this? Those of you working along, or? All right, so this is a little bit tricky here, but I basically want to do the same thing, but right, all these have different criteria, right? This would represent the number of industries with a less than $100 wage differential and below 10% union membership. Well, I still want to keep looking through the same variables, and I'm still using the same cutoffs. So what I'm going to do here, and if I try to highlight all of this and hit my F4 or my Alt T, it won't work. And that's because there's equal signs and things in here. So I have to select these. I'm just going to freeze everything, right? So I'm going to select these, freeze those cell references, select this guy, freeze that cell reference, right? So now when I copy this, it should never change, right? So if I copy this over, I should get the exact same value. None of those cell references should have changed. If I copy this down, right, it should be those same cell references. Nothing should change, right? All I did was put $signs in front of all those references. Yeah.
How do you freeze on the Mac again?
Command T, I believe, is a shortcut. Now, another way you could have done this, so I'm going to undo my changes here real quick. Oops. If instead of freezing those and copying, if I highlight my formula, right click and hit copy, now I got to hit enter to get out of it. I can actually go here and let's just say it was blank. Right? And once I click on a different cell, if I then paste, right, into that cell, notice it didn't update any of my cell references. I can't drag it over, otherwise all those update, right? So I can do it this way, and it doesn't change any of my cell references, and everything works great. But if I would have just dragged it over, well, notice now I'm getting 0 because it's updating my cell references to these goofy columns and things that don't even have data in them. So 2 ways of doing the same thing. Oops. One was just to click on the cell so I can see the formula, highlight it, hit copy, go to the other cell, and then click paste, right? Right click and hit paste. Or I could have froze everything and then just dragged it over and down, right? That's probably the easiest way I would think to do it, especially since you would have had to copy and paste into 3 different cells here, but really doesn't matter, okay? Any questions over kind of anything I said there? It might be best just to freeze the cells just because it reinforces the idea that that's what makes it so that those cell references don't change, no matter how you copy it, right? Whether or not you drag it across, highlight it, copy and paste, if you've got those cell reference kind of those dollar signs on the cell references, it'll never change. Okay. So I did that because I want the same setup, but in this category, I only want to count it if it has less than 10% and a wage differential of more than $100. So now when I'm looking at that unit membership variable, I don't want to count it if it's greater than or equal to. I only want to count it if it's less than 10%. Right? But I still want to be using that check for the difference in earnings of is it $100 or more, greater than or equal to 100. So all I do is go in there and change that one equality. And now it gives me the number of industries that fit these criteria. I then have to go in here. This one, it's going to be, is it 10% or higher? So that one I can leave the same. But is the wage differential less than $100? All right, so I'm just changing that equality sign to match up with the row or column heading or label, however you want to think about it. And then this last category, it will be below 10% and below $100. So these I will change to, is it less than 10%? And is it less than that cutoff of $100? Okay. So I just went in, updated my equality signs so that they match up with my row and column heading. Okay. So now I've got, hopefully, right, I've counted every single observation. Okay. So just like the contingency table, once I have the top 4 left cells, well, if I add the number of industries that have 10% or higher union membership and had $100 or more wage differential to the industries with below 10%, but had a wage differential of $100 or more, that would just count up the total number of industries that have a wage differential of $100 or more. So I can add across the rows and down the columns, just like I did for that contingency table. So I'll, use that sum function just to add up those two numbers real quick. I could have just put equals this number plus the other number. It doesn't really matter. And then I'm going to drag this sum function down so that it adds up the next row. I'm then going to add down the columns using that sum function, right? Just adding up my two values here. I'm going to drag that across to add down this column as well, right? So I'm just adding across the rows and down the columns using that sum function. So if I took every industry in this data set that had $100 or more wage differential, and I added that to the number of industries with a less than $100 wage differential, what should these two values add up to? That would just be every single industry in my data set, right? An industry either has a wage differential of $100 or more or a wage differential less than that, right? So it's counted one time in one of those groups. So if I add these up, right, these totals, I should get my total number of observations. What's one way I could check that real quick? Do you remember a function I said we can check to get what the total number of observations is pretty quick? Yeah, just that count function. I then just highlight any of my variables. I'll just highlight this first variable, hit enter. And sure enough, I got the total number of observations there. If I don't have the total number of observations here in this contingency table, I made a mistake somewhere. I probably left an equality where I shouldn't have, or I forgot one where I shouldn't have, right? You can imagine if I was going through and changing these, and I don't know, let's say, I don't know if this one will change it, but okay, yeah. If I forgot the equality there, and not up, missing a few observations, I go back in. Oh, it was greater than or equal to that 10% here. Okay. Okay, now I've got every observation. Okay. Any questions up at that point? Yeah.
Can I just see your formulas for the
Up here?
Yeah.
Yep. Right, so we had those two variables selected. And then kind of our equalities line up with whatever the row and the column headings are. So those will be different for each one of those 4 cells. But then after those equalities or inequalities, we're just using these cutoff references that we had put up in column O earlier. Any other questions? Yeah.
I but I got different numbers. I got 68 for the less than 100 and 10%. And I got 185 for the top right. and
So,
then 260.
My guess would be, are you making sure if we have the equality here, it gives me 185? So there shouldn't be an equality on this one. All right, so we got to be careful with our equalities. Notice here it's 10% or higher. So here I should have greater than or equal to 10%. But on the other one, when it's below 10%, I should be using just a less than sign, not less than or equal to. I'm guessing that's what's causing the slight differences there. Yeah, and that's an easy thing to do. We have to make sure that our equalities, right? It's A and A complement, right? So that equality can only be on one of them. Any other questions? All right. So I've got all these frequencies now. Well, I wanted a contingency table, right? We were dealing with probability. So how the hell does this help me, right? Well, I mean, if I know that there's 221 industries that have 10% or higher union membership and a wage differential of $100 or more, and there's 735 total industries in my data set, if I chose one at random, what's the probability that they meet this criteria? Well, it would just be 221 out of 735. So when we have frequencies set up for these different combinations of event A and B and their complements, to turn these frequencies into probabilities, all we have to do is take the number of industries that fit that criteria and divide it by my total number of observations, right? So that's kind of anytime we have probabilities, and once we get into this idea of Bayes' theorem, which is the next topic after we get done with Excel here, anytime we see a probability, there's really a frequency floating around in the background. That probability just represents some frequency divided by the total number of observations, okay? So I basically want to go through and do that for every single one of these cells up here. And I'll kind of show you, on the Excel assignment, usually what I do is if I give you the labels, right? I kind of had this table up here. Let's say even when it was blank. If I copy it and then come down here and paste it, whoops, and then just delete everything. Well, now I don't have to retype all my labels, right? They kind of match up with whatever the table I had before was. So I think in the assignment, I'll give you a Word document and it kind of has the table in the Word document. You can copy and paste that right into Excel so that you just have all the labels and the boxes set up correctly. Saves you a little bit of time. Now, if you try to copy and paste it from the web browser, was it someone in this class who stopped by my office and we couldn't figure out why it wouldn't copy and paste? I'm looking to see if I remember. No, they're not in this class. But if you just try to copy it from the web browser and paste into Excel, it like treats it like a text delimited file and it just puts it all into one cell and it just looks like gibberish. You have to download the Word document and then from Microsoft Word, you can then copy and paste it over into Excel and it'll get these labels in there for you pretty nice so that you don't have to type them all in. But regardless, what we wanted was that frequency divided by my total number of observations, right? So I want to do this for every single one of these frequencies, but what do I have to do before I do that? Before I start copying this over and down? Yeah, I want to divide each one of them by the total number of observations. So I never want that cell reference to change. As I copy this over, I want the frequency to update from K9 to L9 and then to M9, right? But I never want that total number of observations to change. So I'll put $signs around that, okay? Now I should be pretty set. And if I forget to, I'll be reminded pretty quickly because I'm going to start getting values in this, these error messages. So I go back, oh yeah, I need to freeze this, right? Because if I don't freeze that, then when I get down to here, it's using blank values, right? So now when I copy this over and down, okay, now things are starting to look okay, right? And this cell down here, once I get to my contingency table, well, this should always be the total number of observations over the total number of observations. So this should always be 1, kind of representing the entire experimental outcome space, right? And then here's the probability of event A, here's the probability of A complement, probability of B complement, and then the 4 intersections that match up with whatever row and column headings we have. Okay. Any questions over this? I think since I'm behind this thing, I can have my mask down. So I'm going to stay like this for a little bit because I feel like I sound probably a little bit easier to hear and I can breathe. So, all right. So are we okay up to this point? Okay. So, these look a little bit messier than the tables that we were looking at on the slides, right? But we can still use them to find some pretty interesting things. So I had a couple things that I set out ahead of time, and I might come up with a couple, just off the top of my head here. But let's say I wanted the probability that if I selected one of these industries at random, that their union membership is 10% or higher. All I have to do here is put an equal sign. I don't even have to type in the probability. I know that that's just 10% or higher. It's that 0.39 right there. All right. Hit enter. What's the probability it's 10% or higher and the difference in wages is $100 or more? Once again, well, that's just, is it 10% or higher? And then those top 4 left cells represent the intersections, or this and this. So 10% or higher and $100 or more wage differential. It's just that 0.300. Right? What if I wanted, what's the probability that I see $100 or more wage differential given it's 10% or above? Well, if I want a conditional probability, we said I can rewrite that as the intersection of the two events divided by what I'm conditioning on. So if I want the intersection of these two events, I just want $100 or more wage differential and 10% or higher. But then I'm going to divide that by, well, what am I conditioning on here? I'm conditioning on the fact, whatever's on the right-hand side of that line, I'm telling you, well, given that the industry has 10% or higher union membership, so we'll divide by the probability of that. So the probability of having 10% or higher union membership, you just go down to that total. Okay. And the idea behind this is, once you tell me to condition on this, actually, let me get out of here real quick so I can make this a little wider so we can have this on one line. Once you tell me that I know I'm looking at an industry that has 10% or higher union membership, if I look at that, well, I know then I'm in one of these categories. So of those 39%, or right, the probability of 0.39, that when I selected an industry at random, it had 10% or higher union membership. Of those industries, only 0.09 had a wage differential less than 100, and 0.3 represented the ones that had $100 or more. So I know that if you tell me that the industry has 10% or higher union membership, it's more likely the wage differential is $100 or more than being less than 100, right? You can kind of see that once I condition, I'm like only looking at that column, right, of my contingency table. Okay. I could then do the same thing, but condition on the other thing. So given that it's below 10% unionized, now what's the probability that it's $100 or more wage differential? Well, once again, it's the intersection of these two. So $100 or more, but below 10%. But now I'm going to divide by what I'm conditioning on, which is having below 10% union membership, which will just be down here in the total. And I can kind of see here, so about 60% of the industries have union membership below 10%. Of that, kind of 0.6, 0.25 has these really high wage differentials, 0.35 has lower wage differentials. So not as much of a mismatch as kind of when I was looking over here at the industries that had 10% or higher. Right? But I can find both of these conditional probabilities. So what is this telling me? This is telling me that given that I know that there's a low percent of unionized workers in an industry, the probability that the union can get their wages to be $100 higher than non-union workers is only about 0.4. However, if they're in an industry that has high union membership, right, given that I know that they've got 10% or higher, the probability they get $100 or more wage differential rises up to 0.76 as opposed to 0.4, right? So, having a higher percent of your industry unionized, if you're a unionized worker, it's more likely you can expect to be making $100 more than your non-union counterpart, right? Almost doubles the probability, right? 0.4 to 0.76, 77, right? So this kind of tells us the relationship between, unionized, more unionized industries, and then that wage differential. But there's a pretty strong, there's going to be some type of dependency there, right? And I could check the law, okay, here I have my conditional probability. I know they're independent events. If this is the same thing as the unconditional probability of making $100 or more. So that, if I think about, is up here, 0.55. Well, that's not the same thing as 0.44. So these would be dependent events or not independent events. Okay. Any questions over or kind of how we use it? I mean, this part really doesn't have to be done in Excel. I could do this by hand, but as long as I have the values in Excel, why type these out? Why try to round them to the 4th or 5th decimal? I'm just clicking on the cells here, right? Just clicking on the cells to get those numbers. It makes it a lot easier. Okay. And I can be a lot more precise. Any questions over anything there? What if I tried this, or what if this was a little bit different? Okay with that? Okay. Anything else? Oh, I want to show you a couple things here. So notice when I was using that count ifs, like for your assignment, technically, you didn't have to use cell references here. You could have like typed in the 10, you could have typed in the 100. Doesn't change anything. I'm going to undo those results though. But if I use cell references, right, then if later on I want to change things, and maybe I don't put 10 and 100 here in my labels, I just put like high union membership and low union membership, and then I want to play around with the cutoff value. Well, maybe I want to define high union membership as 15% or higher, right? Updates my frequencies, updates my probabilities, updates my conditional probabilities and things that I found down here. Now notice if I'm looking at 15% or higher, I still see kind of that difference in those conditional probabilities is still pretty large. But I could play around with this, I could do 150, like get some different results or whatever I want my cost to be, and everything automatically updates, right? So that's why I always kind of show you how to use the cell references, because in practice, this will save you a lot of time if anything ever changes, moving forward. I can have one Excel spreadsheet, and then, maybe every quarter my boss tells me, we chose different cutoffs to be interested in, like, the differences here, and I can kind of play around with them. I don't have to redo all my work. Right? Any questions over anything else that, kind of from this Excel example? Okay, so I'll probably splice this out of the lecture. I'll leave it in the lecture, but I'll also put up an additional one that just has what we did right here. So you can kind of go back and just have the Excel in one video and a little bit easier to find. I don't know if I'll get that done before I go home today, just because I don't know, the video editing software I have takes forever to like repackage it so I can put it up on YouTube. So it usually takes 10, 15 minutes, at least the free one that the university gave me. So I'll kind of maybe do that tomorrow if it's taking a little bit of time, but I will get that up there. I also, and I think I have it in here, but I put up another file. It was called probability tables. It's the same idea. It's just me working through a different data set. Work done on a different data set. So I had some cutoffs up here. I was using this ASVAB score, which is like, say think of it as like the SAT, but it's some measure of like your skill aptitude, right? So the more if you're above the 50th percentile, you can think of these individuals as a little bit more intelligent, perhaps. And then I have whether or not someone used cocaine. You can kind of come up with, a fun little example where you can do the frequencies here, turn them into probabilities. I did the same thing, but use the marijuana variable and its relationship with these ASVAB scores to create another contingency table. And then you could use these to find different conditional probabilities. But it's just a different data set that kind of has, the same kind of thing that we just walked through right now. Okay. All right. So if there's no more questions about the Excel, we'll kind of go back. How much time do we have? At 20 minutes? I'll come back to that at the end. So I want to introduce this. We'll really hammer this idea on Monday. But at least want to introduce the idea of what Bayes' theorem is now, so we don't get behind too much. So this isn't overly important. Bayes' theorem led to this broader thing of Bayesian kind of statistics, which is a little bit different. If you like were over in the stats department, probably when you were like a senior, they might start teaching you that. Basically, the basic idea is you have the probability of some events going to occur. You then run an experiment. And like this is usually based off of historical data. You then run the experiment, look at the outcome, and then update your probability that that event is going to occur, right? If I think that the probability is, if I roll a dice that I see a 6 is 0, but then I roll a dice and I see a 6, well, I should update that probability. I shouldn't just leave it as 0, right? I know that it can't occur. So what we need to have for the setup of these types of problems is two states of nature. So I'll kind of write this as S1 and S2. But these really are almost like complements of each other. So a lot of the examples that we'll use, it's pretty obvious, right? So I'll do things like, you actually are either guilty or not guilty of a crime, right? There's some true state of nature. We try to get at that with like juries and evidence, but ultimately you're guilty of a crime, even if you're not convicted or you're innocent of it, right? I'm sure we're all guilty of things that we haven't been convicted of, right? So I'm either guilty or I'm innocent. That is the true state of nature. But we all don't really know if you're guilty or innocent of something. So, and I'll come back to this in a second. So what we're going to do is we're going to look at some outcome of a test. For if you're guilty or not, that outcome is what the jury finds you. Does the jury find you guilty or not, right? If it's something like HIV, I'm either HIV positive or I'm not, right? I'm one of those two states of nature. I'll then run a test, look at the outcome. If the outcome of the test says positive or the outcome of the test says negative, that gives me some information about whether or not you likely have HIV or not, right? That's the whole reason I'm doing the test. I can't actually look at you and like see your blood and see the molecules, but I can run this test, right? And they're not 100% accurate, but it does give me some indicator of whether or not you have the disease or not, right? So we'll have some state of nature and its complement. So pregnant, not pregnant, HIV positive, HIV negative, guilty or innocent, right? Well, I said these states of natures are kind of like complements. We said before the probability of an event plus the probability of its complement. That was the idea. We have this circle, everything outside the circle. It fills up the entire experimental outcome space. So the probability of an event and its complement always add up to 1. So these two states of nature, because they're complements, those probabilities will add up to 1. Right? Okay. So we've got these two states of nature. We know that those are the only two things that you could be, right? You either have a disease or you don't. You're either guilty or you're not. You look at the outcome of this test. You see, either positive or negative, right? Or guilty, not guilty, right? Usually the outcome of the test is going to be very similar to whatever the states of nature are. It's just that, it's not that you are guilty or not. It's that the jury found you guilty or not, right? It's some outside test. So I said from the last slide, I don't know why I said that. I think I had a slide and I'm moving around. But we might be interested in something like, what's the probability that if I see the test result, E, come back that you're HIV positive, what's the probability that the true state of nature is that you actually are HIV positive? Because that's not going to be 100%. Because there are false positive tests. So if I see a positive test result, it could be that the person actually doesn't have the disease, right? So I want to know that if I see a positive test, of the people who get a positive test result, what proportion of them actually have the disease? What proportion of them actually don't? Okay. All right. So, I'll put this in the context. I'll use kind of the HIV example to kind of set us up as our first example to look at. So what's the probability that given this test comes back positive, what's the probability the person actually is HIV positive? All right, so that's what we're going to be kind of looking for. So I'll write this out. We'll think about what our state of nature is and what our outcome of the test is going to be. So what I just said there was, given that the test comes back positive, what's the probability that the person actually is HIV positive? Well, I could try to rewrite this using my multiplication rule. So it'll be the intersection of these two things divided by what I'm conditioning on. So the probability of E, or the probability that I see this outcome of the test, it's kind of hard because I don't actually know that. Right? I might know like the false positive rate or the accuracy rate, but if I just administer it to someone at random without any information about whether or not they have the disease or not, I usually don't directly have the probability that I just see a positive test result, right? I might know the probability I see a positive test result for someone who has the disease, or the probability I see a positive test result for someone who doesn't, but I don't just know the general probability that you have a positive test result. So we're gonna have to break this equation down, because a lot of the times we don't have the information on the right-hand side that we need, right? Well, if I just start to use some of the definitions that we've had in the past, I know that I can rewrite the intersection of two things using a conditional probability times the probability of what I'm conditioning on. Well, now the problem is I haven't solved anything because this still has the probability of E in there, and I just said we probably don't have that. But remember, order doesn't matter. So if I rewrite this as the probability of E given S1, right, I flip these, well then, to get this intersection, I also could take this conditional probability, notice I'm conditioning now on the state of nature, not the outcome of the test, and multiply by the probability of what I'm conditioning on, which is the underlying state of nature. So that just comes straight from our multiplication rule. Notice that would allow me to plug this in for my numerator. And then here is where it's a little bit, we haven't really talked about this yet. I think intuitively, if I want the probability that I just see a positive test result, remember behind these probabilities, I said when we were looking at Excel, there's like frequencies floating around. So you can almost think about, to get the number of total positive tests, I would take people who have the disease and get a positive result, and add to that the people who don't have the disease and get a positive result, right? That would cover every single person who could see a positive result. So once I break that down into those two groups, well, I usually don't have these intersections necessarily, but I can break those intersections down into conditional probabilities times what I'm conditioning on. The conditional probability of these two events times what I'm conditioning on. And once we get it to this form, I can plug this into the denominator. I think I've got my colors matching up. Right. So I'm just plugging, actually, this happened last class, I forgot to save it. This green box should be up one, right? This was the one that we're plugging into the numerator. So I tried to get my colors to line up here. This green box should be moved up one. But I'm just plugging things in so that I can solve for what I originally wanted, which was the probability of a certain state of nature given a certain outcome of the test, which is what I had here, right? So this was just my outcome of the test was I saw positive. My state of nature one was being HIV positive. Okay. So you're never gonna have to like reproduce this every time. This final equation we have here is what we'll call Bayes' theorem. So what I could then do is kind of write this out in the context of my example. So the probability of S1, well, my S1 is being HIV positive, times the probability of E, which is that I see a positive test result, given S1, which we already said was being HIV positive. Now, one thing you'll notice here, and I'll kind of mention why in a second, this first part of the denominator is exactly the same as my numerator. So for the sake of saving room here, right, I could write this exact same thing. It's the same thing as the first part of my denominator. And then I'll add to that the probability of what? S2. Well, if my S1 was being HIV positive, my second state of nature would be being HIV negative. Yep. Times the probability of E, which was this positive test result, given S2, which we had just said was being HIV negative. Okay. So I've got this written out in the context of my example. Just use this general form of Bayes' theorem to kind of write out my specific example, just to make it a little bit easier. Because now when I go to look at the information that I have, all right, I can just start plugging in the probabilities into that equation once I find them. So it might be something like, here we go. So it might be something like this. I'm given the probability that someone has HIV, right? So if I look at historical data, if I was to choose an American at random, the probability they have HIV is just a little bit below 0.5%, right? 0.00, or just above 0.5%, 0.006. Well, if I then use some things that I know, right? We already mentioned, if I take the two states of nature, their probabilities have to add up to 1. So if my first state of nature is being HIV positive, what would the second state of nature's probability have to be? Probability of being HIV positive plus the probability of HIV negative should just equal 1. So what's the probability I'm HIV negative?
Would it be 0.994?
Yeah, just 1 minus that 0.006, right? So I know these two have to add up to 1. The two states of nature, I'm either have the disease or I don't. So if I take those probabilities, they have to add up to 1. Okay. Any questions on that? The other one that maybe not quite as clear. If I'm conditioning on the same state of nature, those conditional probabilities for the two different outcomes of the test also have to add up to 1. So think about it this way. If I take everybody who has HIV, right, I'm conditioning on the state of nature being that they're HIV positive. Well, given that information, the probability they get a positive test result might be something like 0.9. Well, then given that they're HIV positive, what's the probability they get a negative test result? The probability I saw a positive test result when I'm HIV positive is 0.9. The probability as an HIV positive person I see a negative test result would be 0.1. If we assume, and what we're assuming here is we don't have inconclusive tests, right? It's the first test that gives us a result, if you want to think about it that way. So if we condition on the same state of nature, the conditional probabilities for the outcomes of the test, the two different outcomes, have to add up to 1 as well. So if we condition on different states, it doesn't tell us anything. We don't have any clue what those probabilities add up to. Okay? So if I'm given a piece of information like this, where I'm told, okay, for a person who is HIV positive, the probability that the test comes back positive is 0.999. So really what that's saying, and usually like on the exam or in the homeworks, I try to use a little bit more pointed language of like, given that this is true. But what this is telling us is that for someone who's HIV positive, the probability that the test comes back positive is 0.999. Well, notice, if I condition on that same thing, but I'm looking at, does the test come back negative? What should that probability be? Conditioning on the same state of nature, the probability an HIV positive person gets a positive test result is 0.999. So the probability an HIV positive gets a negative test result would just be whatever gets us back up to, right? Or whatever adds up to 1. It's the only other outcome that that person could see. And then we're given one more piece of information. Given that someone is HIV negative, the probability that they see a positive test result is what? 0.01. And I could do a similar thing here. If I condition now on this different state of nature and look at the other outcome of the test, I can come up with that probability as well, because these have to add up to 1. For the sake of time today, I won't go into that. But you can see here, I've already got everything I need, right? What's the probability that someone's HIV positive? 0.006. Given that they're HIV positive, what's the probability the test comes back positive? It's a really accurate test, 0.999. You have written over it. This was the exact same thing as the numerator, so I'm plugging my values there. What's the probability someone's HIV negative? I wasn't directly given that, but we said because the two states of nature add up to 1, I know that that's going to be 0.994. And then given that someone is HIV negative, what's the probability they get a positive test result? Well, those were like our false positives, and that was at a rate of 0.01. So if we plug all those values in, right, we can find the probability that given we see a positive test result, the person actually has HIV. And this is kind of an interesting one using Bayes' theorem, because a lot of the times when we look at this, when we look at the end result, we get a really non-intuitive result. So I already had this written up on the board. We wrote it out in the context of our example. We just started plugging in the probabilities that we were given. Whoops. We plug all those values in, we get about 0.38. which seems pretty wild, right? Like if I were to administer HIV tests at random, right, to every single person in the US, for everyone who gets a positive test result, only 38% of them would actually have the disease. And the idea behind this is because what that numerator, so what these two groups represented, right, was everybody who had HIV and was correctly identified as having HIV. Here was everybody who didn't have HIV, but got a false positive. So when we add those two together, that's everyone who got a positive test. And then here our numerator was just everyone who had HIV and got a positive test result. So it's like the number of people that had HIV and got a positive test result out of just the number of people who got a positive test result. And the reason why that probability gets so skewed is because not many people have HIV. So even though that we're almost perfectly identifying every single person with HIV with this test, they make up a much smaller number than the vast majority of people who don't have HIV but are getting false positives. So I always try to like link this up. You know, these are probabilities, but we can think about the numbers or the frequencies behind them, right? So if we think about our two groups, we have people that got a positive test result and had HIV. So if I have HIV, that was probably 0.006. So if we just use the number of 300 million to make it kind of easy, that's how many people in the US, I know it's a little bit higher, but about 0.5% of that would be 1.5 million people, right? We then almost perfectly identify all those people, 0.999. So it's a little bit lower than 1.5, but really we're able to get about 1.5 million people that have HIV and correctly identify them as having HIV. The other group of people we have, right, 0.994% of people don't have HIV. So if we just administer this test to everyone, we're going to get about, just below 300 million people, right? We actually have what, 298.5 million. Well, then 1% of those are false positives. So I'd actually end up with 2.985 million, or approximately 3 million people would show up as a positive test result, but they wouldn't actually have HIV. So whenever you have this like disease, or if we're looking at crime rates or something, or guilty or not guilty, anytime you've got one of the states of nature has a really small probability of occurring, even if your test is really accurate at identifying those people, and your false positive percent is pretty low, right? It doesn't matter as long as that is skewed so that one of those states of nature is really, 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 really unlikely. You're going to end up with the outcome of the test doesn't tell you much, because out of these 4.5 million people, 1.5 million of them actually had HIV, but 1.5 out of 4.5 is like, roughly, so 3 out of 9, so 0.33. Right? And if we don't do as much rounding as I did here, we do get that 0.38, right? It's a little bit higher, but I think this kind of, think about the frequencies maybe help this connect a little bit more. All right, so we'll come back to this on Monday. I'll kind of show you how to do a probability tree. Before we get out of here, I did want to go back as long as we've got a couple. Yeah, we got a couple minutes here. So one thing I thought was kind of interesting, kind of related to what we were talking about with independent events. So if I'm not going to use this as an eye clicker, but anytime I'm flipping a coin, right, the probability I get heads is 0.5. It doesn't matter if I see 5 tails in a row, the probability I get heads on the next coin flip is still 0.5. So a lot of people think that, well, in the long run, this has to be a 50-50 breakdown. So if I see 5 tails in a row, it almost has to be them going to get a heads in the 6th one. Well, no, that's over the long run. It says nothing about the very next coin flip. So you can run these simulations in Excel, and the probability you see a heads come up after 1 tails in a row, 2 tails, 3 tails, 4 tails, it's basically 0.5 every time. But I had, I limited this to 10,000 coin flips. If I did an infinite number, this would be exactly 0.5 every time. So way back in the day, one thing people fall victim to is something called the gambler's fallacy. So there was this casino, and a roulette table, it's basically 50-50, whether or not it comes up red or black, right? And so black came up 26 times in a row. So after about the 8th or 9th time of seeing a red red come up, everyone starts falling victim to that gambler's fallacy, which is, well, it has to be 50-50. So, after it came up 8 times red, the 9th has to be black. Well, no, it's still 50-50. Probably still 0.5. So you should still bet accordingly. Well, people didn't. They started after 8 or 9 times of black coming in a row betting on red, and then they lost. Well, it came up black 10 times in a row. The 11th one has to be red. So they bet red, they lost, right? This continued all the way up to 26 times in a row. The casino made a ton of money. All the patrons lost a ton of money. And it's because if they're independent events, the probability doesn't change no matter how many number of previous successes you had, or how many number of times you saw black come up, right? The probability that black or red comes up this time is still 0.5. Okay? So if these are independent events, you could really take the probability that I see red, which is 0.5, times the probability I see red in the second flip, 0.5, all the way up to 26, take 0.5 to the 26th, and that's how unlikely it was that you would see black come up that many times in a row. So I have a kind of fun example relating to some of the stuff we talked about today. I'm a little bit over, so I'll let you guys get going. Look for that second Excel assignment, that Connect assignment, start working on those early. So when we get closer to the exam, you'll have time to start reviewing for that. Other than that, have a good rest of the week and weekend, and I will see you guys on Monday.